Welcome to the broadcast. Today we'll be talking about the smart robot revolution. And I'd like to thank IEEE Intelligent Transportation Society, as well as Women in Engineers for sponsoring and organizing this chat. And also special thanks to Kiana Tennant and Emily Sopensky. So we have here at Stanford a live audience in addition to the online audience. I welcome questions from the audience at any time throughout the talk. This is really meant to be more of a discussion. So I'd like to start by telling you sort of my personal story about how I got involved in robotics. So it started back in early 2000s. I realized that basically our world is full of is filled with sensors and computers all around us. And mind you, this was 5 years before the iPhone came out. But it was already clear to me that this was there and we were only going to get more of it, and that it was very powerful. You can do a lot with it. So what better way, I thought, than to join the Stanford robotics program. So I went to Stanford and I spoke to a very famous robotics professor who will remain unnamed. And he's indeed well respected in the field. And when I told him about my excitement about robotics, his response was, you're wasting your time. Robotics is dead. For the past decades, there has been lots of research, but none of it is able to get out into the real world. And that people are talking about maybe making robotic elderly assistants, but all of that is just wishful thinking. It won't happen. So luckily, I didn't listen to his motivational message and decided to do robotics anyways. So what was it that I saw that he didn't see? I saw that sensors and computers, or sensors and brains, are really fundamental. And they're fundamental in order for robotics to be able to get out into our world, because that's what is required for them to understand our world. In robotics, sensors plus brains is called perception, and basically that's a process that takes sensory inputs and converts them into useful information about the surroundings. And I see perception basically as the enabler that allows the rest of robotics to reach real-world applications. So in some sense, perception is the bottleneck through which the rest of robotics and AI research has to go through in order to reach the real world. So it turns out that perception is really hard. You can think of computers as sort of having an extreme case of Asperger's. They are very focused on data, they understand the data, but they're not able to sort of draw a bigger generalization out of it. They're not top-down thinkers like most of us are. And in fact, they're having a difficult time going from the bottom up. So we have to teach them how to do that. And as an example, as you watch this broadcast, you see a video of a person giving a talk. When computers look at this video, all they see is a bunch of individual pixels of different colors. So let's have a look at how perception works. Basically, you can think of perception as a process that takes in data and from the data estimates certain parameters that describe the world. So no quantity can be measured precisely. Of course, so says the uncertainty principle, but even more than that, there is noise in all the sensor data, there is interference, there is inaccuracies in the way we model things. So it is not possible to precisely measure any quantity, and it's all the way down to the fact that computers have floating point precision and floating point error when they make computations. So if you can't measure things precisely, then the next best thing you can do is to use probabilities. In other words, you can't tell the exact answer, but you can, for every possible answer, you can say the probability of that being the correct answer. So, for example, as you watch the broadcast, let's say your job is to track the motions of my head. And you can do this by sort of figuring out, by parameterizing it with, let's say, X and Y position of my head on the screen. And you can say that the probability is really likely for the position to be here, and then the more you move away from the actual position, the less likely it becomes. So that's the probability distribution, which is called the belief, the probabilistic belief, or the Bayesian belief. So these probability functions are very complex. In fact, if you were to plot them, they look like a complete mess. And the reason why that is actually because of the way the world is. So in fact, Mandelbrot had sort of foretold it in his book, The Fractal Geometry of Nature, in which he explains that although mathematicians like to focus on simple, smooth functions, most functions are not smooth, and in fact, functions that arise from nature are not smooth. So I'd like to read you one quote from his book. Clouds are not spheres, mountains are not cones, coastlines are not circles, and bark is not smooth, nor does lightning travel in a straight line. So I think that basically sums it up. Our world is not smooth, and because the probability functions in robotics are sort of a reflection of the world, because they encode the properties of the world, then this non-smoothness of the world makes it into these probability functions, and they also look very much unsmooth on any scale, whether you look at large scale or close up. So because of this, smooth functions for estimating or approximating these probability distributions do not work well. And therefore, recently, most of robotics research has turned to use point-based methods. For example, importance sampling, particle filters, or even grid methods. So in Monte Carlo methods, the points are sort of randomly arranged. In grid methods, they're arranged in a grid. And at each point, you measure the value of the function. And this, collectively, these points and the values become the representation of the function. So the good thing about that is that, of course, this can represent arbitrary functions, and it can represent the types of messy functions we get. The bad thing is that, could we close the door? I think it's getting a bit noisy. So the bad thing is that the computational complexity of these methods goes up exponentially with the number of parameters that you're trying to estimate. So problems can very quickly become intractable. On the other hand, these methods were sort of just simply imported from other fields into robotics, and they were not specifically made for the types of functions that we have. Because the functions we have are not arbitrary. They have properties to them that are dictated by properties of the world. And these are things that we can use. So my contribution here is that I sat down and I looked at these mathematical functions, and I figured out methods to estimate them much more efficiently. And I also use point-based methods, but that are specialized and optimized for the robotics applications. And these methods end up being several orders of magnitude more efficient than the basic methods. And of course, several orders of magnitude is the difference between solving a problem on a supercomputer or solving it on your mobile device. So next, I'd like to go and show you some videos of robots from my work, and hopefully along the lines we'll be able to understand more about perception. And please feel free to ask questions at any time during the videos or going forward. All right. So I like to start with this one here. Let me stop it for a second. Okay, perfect. So I like this video because it is very slow, and so it gives me ample time to explain things. So what you see here is the robot has the task of localizing an object. So this object is a cash register. The robot knows the geometric shape, but it doesn't know where in the space and how it is positioned. So it needs to figure that out. And it has to do that based just on touching the object. So the only sensor that it's using is this blue cylinder here, which is a force and torque sensor. So let me get that going. So what it's doing, it's simply randomly probing through the space, and each time that it detects a contact, it runs the estimation method, estimates the probability function, looks at it to see if it has enough information to estimate the parameters with enough certainty. If not, then it goes on to collect more measurements. And on average, after 12, 14 measurements, it figures out where the object is, and then it can go ahead and manipulate it. Now, of course, this is quite slow. There are several reasons for this. So one reason is that we're using only a single point of contact, a single finger. If we used a full hand, then we would get many contacts in a single grasp. And of course, that would expedite things significantly. However, for that, the robot needs to have sensory skin covering the hands. And today, robots don't really have that. In fact, it is an active area of research. And even here in our lab at Stanford, we are working on that and working on using multi-fingered hands to localize objects and to perceive objects and doing that underwater. So the reason to consider underwater environments is because one of the motivations for this work comes from the BP oil spill that, of course, was a big disaster. And it was very difficult to clean up this or to even stop this disaster. And at the end, what helped solve the problem was the robots. It was a remote-controlled robots that managed to shut off the flow of oil. Now you can imagine that if you're working underwater and you have a mixture of oil and water, then it is really very hard to see. So in these conditions, you cannot use vision to figure out where the objects are. And therefore, tactile and touch-based feedback is your best friend for perceiving objects. Now, so if we split this up into brains and sensors, the sensors here are slow, but the brains are fast. The algorithm that estimates the parameters is fast. So we can use the same algorithm on the same problem, but we can just replace the sensor. And as you can see here, with a better sensor or a faster sensor, which is a 3D camera in this case, using the same object and the same model of the object and the same algorithm, we can now track objects in real time, even through very fast motions. Now you can see how this is something that could be used, immediately useful for a number of applications, such as human-computer interaction, gaming, augmented reality, and even movie production. So now I'd like to switch gears and look at a different application. So the video you see here is of an autonomous vehicle, and this was taken at an event in 2007 called the Urban Challenge, and it was organized by DARPA, which is the research arm of the Defense Department. So in this competition, robots had to perform completely autonomously, so there is nobody in the car driving, there is no one remote controlling it. But they also had to reach different goals within this sort of suburban setting, and they had to obey the rules of the road, and they had to also behave nicely with respect to other traffic on the streets. And we had both robots as traffic and human-driven vehicles. Now this event was pretty amazing because when we came in, we didn't know if this was something that was possible. And in the span of a few days, we realized that yes, in fact, this has happened. The robots can enter our environments, understand them, and they can sort of seamlessly fit into them and coexist with us in these environments. So this was really a big deal for all of us. So my job on this project, I was part of the team that built this robot that's called Junior, and that later on sort of evolved into the Google car. So my job on this project was perception, and specifically my job was to detect and track other vehicles on the road. So next I'm going to show you another video from this event. So here, this is the most difficult test that we had at the competition. So in this test, the robots have to repeatedly merge into live traffic, and they kept the traffic pretty heavy, but obviously not heavy enough, so you would have some openings. So a lot of robots got disqualified at this test. This was by far the hardest test. And the reason is because if the robot was too timid and waited too long to find an opening, then it would be disqualified. And also if a robot were too aggressive and would endanger other vehicles, then it would also be disqualified. So now I'll show you the same event, but from the point of view of the robot. So it's exactly the same sequence, but from the robot's perspective. So let me stop it here and explain what you see. So this is basically what the robot sees, or what's happening in the robot's brain. Over here in the corner, you see an image from an onboard camera. Now the robot doesn't use that. This is just for humans, for reference. Instead, the robot is using these white points, and these white points are coming from a 3D laser called Velodyne, which is the big spinning thing on top of the car. And it gives something like 1 million points per second of data. So you can see here that you can see sort of the flat part, which is the ground. You can see some vertical obstacles, which are different structures. In the distance there is a tent that you'll see coming up, and that's a tent where all the judges sit, so you will see that. And then the purple boxes here are outputs of my algorithm, which is detecting and tracking vehicles based on the sensory data that's coming in. There you can even see the judges moving about in the tent. And the audience here is on the other side. I'm somewhere on the other side watching this. Now, of course, this was sort of the event that started bringing the autonomous cars into the industry. you'll see a lot of sort of industry stickers on the vehicle. They were all sponsors. And of course, this project sort of moved on to the Google car afterwards. And a lot of the Stanford team went there to continue working on the vehicle. But besides Google, there are also many other companies that jumped into the fray. Most major automotive companies are now working on autonomous vehicles. And in fact, recently Nissan has announced that they expect to be selling autonomous or self-driving cars by the year 2020. So I'm going to show you probably a few more robotics videos later if we have time left. But now I'd like to talk a little bit more about sort of the current state of robotics, what's happening right now. And so, as I mentioned already, autonomous cars have been a big success. But it's also prompted a lot of other applications to come out and a lot of interest in robotics because people have realized that robots can do these much more complex things. Whereas before they were confined to sort of the strictly controlled environments that they have in manufacturing and where they performed only specifically pre-programmed tasks. Today, every year, basically, all the major players spend billions of dollars acquiring robotics companies and AI companies. For example, Google last year acquired Boston Dynamics, which makes legged robots. And then earlier this year, they've acquired a company called DeepMind, which is an AI company focused on doing deep learning. And Google's not the only one. Apple is spending sort of steadily a few $1 billion a year on robotics. And recently it bought the company PrimeSense, which is the maker of 3D cameras. And in fact, that's a 3D camera that was used in the cash register video. Amazon is another company that's, of course, very interested in robotics. In 2012, they bought a company called Kiva, which is a warehouse automation company. Okay, so we have some questions coming in. So let me just finish this slide and then I'll address the questions. And of course, most recently, Amazon has announced that they're going to have delivery drones that will deliver packages to us within 30 minutes of us placing an order online. And they're saying that they will be ready to do this as early as next year. So you can really see that there is a lot happening. And the government is actually not far behind. So recently, Department of Defense has announced that they expect to reduce the size of the Army forces by 20% over the next 5 years, and that they will do this using robotics. And it is presumed that a lot of that will be sort of autonomous or semi-autonomous vehicles in the convoys. But there will also be robots that will be helping individual units. So let me see. I'll look at some of the questions. Was this robot technology used in a BP oil spill? So yes, the robots were, I mean, if you remember, there were many different attempts to shut off the flow of oil, and all of them failed. And after a while, the thing that worked was sending in small underwater robots that were remote controlled and that were able to actually finally shut off the flow of oil. Okay, another question is, can the autonomous vehicles sense turn signals? So yes, you definitely could make it so that they can detect sort of the lights of the cars because they have sort of a very specific pattern to them. and they can then detect when the light signals are on. That wasn't part of what we had in the Urban Challenge. It wasn't required there. Miguel is asking how much processing power is required for that perception system. So I'm not sure which perception system you are speaking of specifically, but the self-driving cars generally run off of a laptop, sort of an ordinary laptop of today. And of course, we expect that these technologies will only become more and more efficient and computers more and more powerful, so that eventually your mobile device will be able to do these things. All right, so let me move on to what I think is really exciting about what's coming up. So most of the things we've talked about that are happening today are happening either in automotive industry or in warehousing or in manufacturing, where now robots are able to do sort of more complex tasks that they couldn't do before using perception. However, what's going to happen is that the intelligence that is now in self-driving cars, we will be able to see that come into our homes, come into our mobile devices, and really profoundly change the way we live our lives. Recently, there was a market research report that came out specifically focusing on robotics. I was very excited to look at it because it was a market forecast for the next 2 years. And when I looked at it, I realized that it actually didn't have any of the exciting companies that I'm working with today. And so these are all sort of small startups bubbling just under the surface, waiting to come out. And I expect a lot of them will come out over the next 5 years. So we will see a number of things. So for example, an equivalent of a holodeck will become a reality rather than science fiction. Of course, that's going to revolutionize gaming and entertainment, but it'll also affect a number of other areas such as architecture, real estate, even mundane things such as shopping for furniture will be entirely different. And beyond that, this technology also has the potential to be used in medicine. So the doctor will have a much better understanding of the patient's body, and the surgeon will be able to perform surgeries much better and with much better outcomes. And so there is a real possibility for this technology to help save lives. So as I said, all of these things are coming in the next 5 years, and these are things that are actually happening today, and I'm basing this on my experiences with these different companies. So I think we have another question here. All right. So are there questions from either the online audience or the live audience? Yes.
So I think we are very familiar with your work up until your thesis, but I was wondering what specifically you have been working on since then.
Okay, so the question is, what things have I been doing since my graduation from Stanford? So I've actually had a consulting company all along while I was in the Stanford program, but the focus of the company changed significantly, and basically now we're consulting exclusively in AI and robotics applications. And so, as I said, we're consulting with a lot of these companies working on these super exciting things. And also, we're actually working on our own technology, which is going to be doing perception for a lot of these applications. And we're getting close to completion, so we should be able to announce it within the next couple of months. In parallel, I'm also a research consultant here at Stanford, where I help advise some of the students. I give a lecture every so often on perception in the advanced robotics class. And I also help come up with ideas for new research proposals that sort of shape the research of our lab going forward. So now this, I've gone through most of what I wanted to share with you today. So please send in your questions if you have them, or if anyone in the live audience has more questions, please ask them now. And while we wait, I can also look at some, can also show you some more robotics videos. So this is a video of a mobile manipulation robot. This is called the STAIR robot, which stands for Stanford AI robot. And it is performing a similar task to the one you saw with the cash register. In other words, he's trying to perceive the environment by the sense of touch. Except this one has much fewer sensors. So the only thing it can go off are the encoders in the joints. Nevertheless, it is able to very reliably figure out where the door handle is and operate the door handle. And I should mention that although the touch-based perception and manipulation are autonomous, the motion of the platform was done using a joystick, because this was sort of the very beginning of the robot, and we didn't have autonomous navigation yet. Now, in this next video, in the next video, you see the same robot, now slightly updated. And now it is fully autonomous. All navigation and manipulation are autonomous. And so its task is to navigate through our building and to be able to open doors. And one particular thing here is that the only sensor that it will be using is this laser scanner on the bottom, which is just a 2D laser scanner that gives you 2D scans. Now, one of the things it needs to do, of course, it needs to grasp the door handle and be able to open the door. But you can see that the laser is mounted much too low to be able to see the door handle itself. So the only way it can reliably operate the door handle is by localizing within the building really accurately. So it has a model of the building that it previously built. And now it needs to sort of figure out its position super accurately. So in fact, it needed to position itself to within 3 centimeters of a specific spot in order to have enough strength to to turn the door handle. And it needed to have accuracy on the order of a millimeter in order to reliably manipulate the door handle. So this is, of course, a big contrast to sort of what you see typically in robots that are localizing in buildings today. Typically, you see accuracy of, well, somewhere within 50 centimeters. And in this case, of course, we can go down to a millimeter. So that's a huge difference. And typically, millimeter accuracy is reserved for stationary manipulators that are sort of nailed down to the floor, the kind that you find in the factories. But here we can have this accuracy in a mobile robot. And of course, that opens up a number of applications. So things like, of course, it's going to be able to operate elevator buttons, door handles, and so on, all sorts of objects that are statically positioned in the environment. But beyond that, it can help in other applications like building inspection or even construction. because it will be very accurate, will be able to very accurately measure distances. So let's say, for example, you wanted to place pictures on the wall at sort of at regular intervals. So this is a kind of robot that could do that very well, just based off these algorithms. So we have one more question. How did you choose your engineering field? So I must say that I didn't really specifically choose to be in engineering. Instead, kind of what happened was I had a hobby of working with computers and writing code. And then later on, it turned out that actually people are happy to pay me money for this. So I ended up having a job. But then as far as robotics, of course, as I already said, I realized how many sensors and computers we had out there and how much potential that had. And that's how I got interested in doing robotics. Another question is, can you tell us what is entailed by your perception focus? Not sure I completely understand the question, but basically, as I said, perception is the process that turns sensory inputs into useful knowledge about the surrounding environment. And this is what's needed for robots in order to coexist with us in our world, because they need to be able to understand us and they need to understand our environment. The next question is, what blocks of the perception system are more likely to fail? Well, this is difficult to say, of course, and this is something that changes dramatically as people put more and more work into it. I know that in perception, one big possibility for perception to fail was actually the algorithms themselves, because they had a hard time coping with how messy and non-smooth the probability functions were. They would often make mistakes in estimating them. And so I actually analyzed this and I came up with algorithms that can give guarantees that the correct answer will be found and sort of the correct probability distribution will be estimated. On the other hand, of course, when you're working with real physical robots, there are a lot of sort of connections, sensors, and other things. So a lot can go wrong in the pipeline. You can be sort of losing packets off of your cable. And in fact, we had that when we were developing Junior, the autonomous vehicles. And I had to make adjustments so that perception could handle outages of data if need be. All right. So, any more questions, perhaps, from the live audience or from the online audience? Yes.
So humans seem to very seamlessly integrate action and perception together. And I was just wondering if you can talk a little bit about what state of the art is. It seems like a lot now is sort of decoupled doing planning from doing perception. And if you work with this at all in your research, or if you know what state of the art is in this topic.
Okay, great question. So the question is whether robots are able to sort of as seamlessly integrate perception and action as humans are, because we do both things without sort of thinking about which is which and without separating those into separate pieces. And of course, that is very true. And in robots, things are far more sort of compartmentalized because different researchers focus on the different fields. That being said, there is more and more active perception that's coming out, which is combining action, action with perception. And for example, there are planning methods that will figure out sort of let's say you want to build a map of this building, and these planning methods will figure out, well, where do I have the least data, and will try to sort of direct the robot to those areas so that it explores and builds a better map. In fact, I have recently written a chapter for the Handbook of Robotics that is specifically on active perception, perception by manipulation. And it's under review now, and it should probably come out within the next couple of years in the Handbook of Robotics. So there is more and more work that's trying to figure out how to combine manipulation and be able to use sort of each contact for perception, even if what you're trying to do is actually manipulate the object. For example, there is work by Kai-Zhang Xiaos, who used planning algorithms, and they're based on the probability distributions. So they actually can deal with all the sort of the uncertainty that's coming in from the sensors. So her robots are able to both sense the objects, try to turn the objects as they're sensing them so that it is easier to localize them and it's easier to manipulate them. And eventually they manipulate them, and at the same time they're sort of collecting the data. So yes, to answer your question, definitely there are more and more methods that are combining action and perception. The next question is, what were more common perception mistakes during the urban challenge? Well, it's difficult to tell. So of course, when you're developing the system, you start with it sort of not working or working poorly, and then over time you figure out how to make it really accurate and reliable. For example, I started by using just sort of basic methods for estimating the positions of the vehicles. And they failed a lot. So it could take you as long as 12 seconds to recognize, to detect another vehicle that's oncoming. And of course, for oncoming traffic, you don't have that much time. So basically, if it takes you 12 seconds, then your estimate is useless for the purposes of driving. Switching to more advanced methods that I've developed solved that problem. And I think the worst we had was half a second to detect a new vehicle that's coming into view. And that's basically equivalent to the human reaction time. And of course, there were also there was also a lot of experimentation. I mean, we didn't know going into it. We didn't know sort of what are the right sensors, what's the right configuration. For example, MIT's vehicle is notorious for being sort of just covered in sensors. It had lots and lots and lots of sensors. And that's a good thing perhaps to do when you're trying to figure out what will work. But of course, for the purposes of later having a vehicle, an autonomous vehicle, you want to use as few sensors as you can to be able to achieve the task. Because sensors, of course, are expensive, they eat power, and also all this data coming in needs processing power. And so you want to be able, it is really important to be able to get as much information as possible from the data you get. And that saves you a lot in terms of money and power and efficiency. Okay, another question.
Do you know which perception system Google is using?
So the question is, which perception system is Google using? Google sort of inherited the code base from Stanford. And of course, they've since evolved it and developed it into something more. Now, I've been told that basically my work lives on in the Google car. And beyond that, of course, they can't disclose very much, so I can't say much more than that.
Do you look at applying your approach to doing pedestrian detection and tracking in the urban challenge?
So the question is whether we've applied the vehicle tracking techniques from the urban challenge to tracking pedestrians. So that's a fair question, of course. Now, in urban challenge, there were no pedestrians. There were only vehicles on the road. They wanted to sort of restrict the complexity of the problem because, frankly, they didn't know we could even solve that. Since then, however, I mean, in real applications for autonomous vehicles, they need to be able to see both people and vehicles. And since then, people have sort of extended my methods. I proposed model-based methods for detection of vehicles, which not only detect and track vehicles, but in fact, they can produce complete 3D models of vehicles, which actually helps the robot understand the environment and helps the robot track these vehicles more accurately. And these methods have been extended to pedestrians and also modeling sort of moving participants on the road of different types, be that cars, buses, pedestrians, bicyclists, and so on. So that has been done. In my own work, for the urban challenge, as I said, the pedestrian detection was not part of it. But I was able to detect and track vehicles of different shapes because I was able to estimate the shape of each vehicle that I'm tracking. The next question is from the online audience. Who was your role model when you were young? Well, so I guess that depends how young. I grew up in a family where my father was a professor of physics and my mother worked as a software developer. So even if I haven't sort of actively thought about them as role models, obviously they shaped what types of things I got interested in and I got to work on later on. As it does basically for all children growing up. And so, and because of this, it's sort of like I didn't really choose a high-tech career. It was basically something that was a natural thing to do. So I guess my parents were my role models. And then later on, of course, in the Stanford program here, my advisor, Osama Khatib, was a role model. In how he's sort of able to combine research, but also have time for other things. And he's very wise about being able to manage your time and sort of manage your expectations of doing research. And another faculty I wanted to mention is Mark Kwiatkowski, who I feel who I really look up to, and I feel that is amazing how he is sort of a generalist. A lot of faculty sort of get focused on a specific area, whereas he seems to know things very broadly, and he can basically talk about very broad topics, even topics that are not in his specific field. And he has a way of doing it that is that's sort of engaging and if he asks you questions during a talk, you never feel like he's sort of attacking you. He's always sort of more provoking a discussion or leading you into a discussion. Another question we have from the online audience. What are a few of your motivators? What makes you excited about doing what you do? So when I was young, I wrote code because I felt it was easy to do, and you sort of quickly put something together that is really useful. So in fact, some of the first programs I wrote were computer games. I wrote a blackjack game for my friends, and then we played it with my friends. And they were really excited about it. And the most exciting feature in it was the AI that I put into the game, which was very simple. It absolutely at random, it would, when you ask him to draw the next card, it would ask you, are you sure? And of course, even though it was random, my friends didn't know it was random. So they began thinking, well, maybe the computer knows something. Maybe, you know, I should rethink my choice. Um, so so I guess it was fun, but I think it also underscores sort of more broadly why I get interested in doing things, and why I got interested in doing things later on. And that is, I am doing them because I care about the impact that they make on the people around me, and on the people globally. So it is sort of the application, the value that these things bring in. And of course, with robotics, it's very much the case that there are a lot of exciting applications that can come out and can truly revolutionize a lot of the things that we do. Yes.
Where do you think lie the greatest challenges these days in making humanoid robots actually useful for kind of more general purposes or for society together? Is it perception, or is it control, or AI, or do we have to make the mechanics cheaper and more affordable? What do you think is this the kind of the field we have to push to make a real big leap?
Okay, so this is a big question. We have a question from a live audience about what's holding back sort of the humanoid robots. What are the biggest challenges in bringing humanoid robots into real world applications? Whether it's energy consumption, hardware, perception, AI, what are the biggest stumbling blocks? So perception, of course, is a big problem, as it is a big problem for all of robotics. And it is very challenging. Autonomous driving, as complex as it may seem, is probably not the most difficult problem. It is more difficult to be sort of in crowded environments in our homes, where there is even less structure. At least on the road, you have the structure of the road, and you have the specific rules that all the vehicles have to follow. That's not true about our homes and sort of yeah, interior environments. So perception clearly is a problem that needs to be addressed and is being addressed. But there are also other challenges that are specific to humanoid robots. One such challenge is to make a robot strong enough to sort of carry itself, but at the same time not too heavy. So it is able to do things like run and jump and carry other things. And that is difficult. We have not seen a lot of robots, humanoid robots yet, that are able to do that. Of course, Boston Dynamics, the company that was purchased by Google recently, is probably one of the only few, if not the only company that has been able to make humanoid robots that are strong and that can run as fast as humans can run, or even faster. So their technology is promising to perhaps solving that problem. And another challenge sort of to all of robotics, to bring all of robotics into our lives, is safety, because basically robots are big machines made of metal, so they're heavy, and if they don't understand things properly, or for some reason they malfunction, then they can be dangerous to the environment. So for example, a self-driving car, if for some reason it doesn't operate properly, it could cause an accident. So making robots safe is is a big concern and a big field sort of in the rapidly growing field in robotics. And in fact, our lab does a lot to focus on that specific aspect. Yes.
How can you ensure that there will never be any accidents with autonomous cars?
The question is, how can you ensure that there will never be any accidents with autonomous cars? So my answer is, I don't think we can ensure that. There probably will be accidents, but the important thing, and the reason to bring in autonomous cars would be if we're able to reduce the number and the frequency of accidents compared to human driving. So if autonomous cars become much safer drivers, and so far the evidence we're getting from the tests performed on the Google car indicate that they are in fact safer drivers than humans, and that helps save lives, even if we cannot eliminate the problem entirely. The next question from the online audience is, what is the best advice you have ever received in your profession? Well, perhaps some of the best advice, although I received it after the fact, is to be very careful about picking your husband. So, in fact, Sheryl Sandberg, who has recently published a book called titled "Leaning In," is talking about a lot of women's issues, and she says the most important decision for your career that you make in your life is the husband that you choose. And I do believe that to be very much true. And so I would encourage young women to look for helpful husbands that will be supporting their careers and will be understanding of their careers going forward. Now, of course, I was already married by that time, but it seemed that I sort of instinctively knew to look for somebody who was really helpful. And now we're working with my husband very closely. In fact, our consulting company consists of the two of us, and we're very happy doing robotics together. What words of advice do you give to young female engineers when you meet them? I'm not sure how much other than the be careful about choosing your husband advice, I don't know how much of the advice I give is specific to females. Actually, all young people entering into the field can use basically the same advice, even if it may be more applicable for women. But a lot of this advice I've learned from my male colleagues, actually, that sort of figured these things out for themselves. And the advice is basically you have limited time in your life to achieve things and to really focus on doing something that's important. So you have to be careful about how you use your time. You have to be basically mindful about how you spend every hour of your time. And you should do everything you can in trying to make yourself more efficient. So what that means in reality is if you have a job where you're not being efficient, you should look for a different job. You should not have a job that does not fully utilize your talent. You should also sort of try to affect the environment, your working environment, to sort of configure it for yourself, to make it so that it makes you as productive as you can be. And also, as one of my colleagues has told me, and I do believe this to be true, choose people, focus on people who are supportive of you, who you like, and who are interested in the same things you're interested. For example, when you're doing research, there are a lot of people out there. They're interested in different things. But you should focus on the ones that are sort of the same mind as you are, and because that will help you be more productive. Okay, so it looks like that's all the time that we have today. So as the final note, I am happy to report to you, and I hope by now you agree that robotics is not dead. And in fact, it has a very bright future. So thanks for tuning in. Thanks again to IEEE Intelligent Transportation Society and Women Engineers for sponsoring and organizing the event. And thanks to the live audience here and the online audience. Thanks for tuning in. You can send more questions to me by email later on. And by the way, the videos that I've shown are available on my website that are linked from the main page for this podcast. And when the video of the podcast becomes available, if you've missed any part of the talk, I will post that online as well so that you can view that. So thanks for tuning in.